Okay, so welcome here, and today is a great honor for me to have Sauro Succi here for this ceremony of the delivery of this Eugenio Beltrami Prize for 2023, because that's as usual in this prize from the MEMOCS Society. They are given some years later.
There is the delay of COVID, which we did not recover.
Yeah. And so, anyway, so first of all, I have to read the Laudatio. In this case, we have a somewhat exceptional Laudatio, because the prize, one of the main support to Sauro come from Giorgio Parisi, who wrote this letter, and the MEMOCS Society decided to use this letter as a Laudatio for this prize. So I read some part of this letter. Sauro has made numerous outstanding contributions to computational physics, applied mathematics, engineering, but his international standing is mostly attached to his groundbreaking work on lattice Boltzmann. I am is Giorgio Parisi, sure that other nominators will cover his pioneering contribution in detail. I'm speaking as Giorgio, unfortunately he's not here today, but was warmly supporting the candidature by Sauro. As in the following, I shall only comment on what I regard as his most unique and far-reaching contribution. He was the one who first saw and actually realized the suspected potential of the lattice Boltzmann beyond its original realm of the physics of fluids. He is directly responsible for an impressive number of major LB extensions, particularly in the direction of soft matter, forms, emulsions, soft glasses, soft flowing crystals, multi-scale problems, and physics, engineering, biology interface, as well as quantum relativistic transport in graphene and subnuclear plasmas, and lately also quantum computing for classic fields. More generally, he has been a pivotal figure in uncovering and deploying the amazing flexibility of the ALB to compute the complex states of flowing matter, which elude the continued description and remain computationally unviable from microscopic methods. This is a paramount advance in statistical physics, as it basically bridges the historical gap between continuum and atomistic mechanics, thereby enabling a vast spectrum of engineering applications across many scales and different regimes of motion, from macroscopic fluid turbulence and all the way down to microfluidics and nanobiological fluids. And there are a list of many prizes already Sauro received, in particular the APS Anesu Raman Prize and the Czech Bernie Alder Prize, and also the ERC grant, which is one of the main achievements of his career. So, in his view of Giorgio, modern science presented three outstanding frontiers: the extremely small, high energy, the extremely large astrocosmology, and the extremely complex. This latter is perhaps less spectacular than the previous two, but it is by no means less profound and impactful for science society, and particularly for the development of modern cutting-edge engineering application. Based on the above, I am absolutely positive that Sauro's work represents a unique and transformative advance to the latter frontier, which qualifies him as a truly ideal candidate for the most prestigious Eugenio Beltrami Prize.
Thank you, Giorgio.
So, here we have a pergamon, and then it's for you, and also
the medal.
Il bello.
Thank you. Well, after the talk, so that I'm sure you don't change your mind.
No, what I mean, no, the price is now.
We cannot change.
Okay. So,
Okay,
any picture?
okay, so thank you very much. Now you have to deliver your talk,
Yes.
so maybe we can.
Okay. So
Maybe you can say 2 words before, but we can start with that.
so can I? Are we on air?
Yeah, we're already on air.
Okay. Thank you so much, Roberto or Giorgio, or how should I call you? I don't know. Unfortunately, Giorgio forgot that he had to give a talk today, so he was not here. But nevertheless, he has been a great friend over the years.
He's out of town.
He's out of town. He's in Peru. So I'm very, very, of course, humble of this honor for many reasons. Some of them are scientific, some other are related to my life, in the sense that the prize is managed somehow as a significant contribution from IAC, where I spent basically the bulk of my career. And so thank you very much to the committee and to my nominators. And what I would like to do today is to, I'm not very much into the mood of giving historical talks, but for the occasion, I think it might be interesting and hopefully entertaining to see how this nice story, the Lattice Boltzmann story, developed over almost 4 decades, I must say. It's rather amazing, but it is like that. Before I enter into the specifics, I did a little bit of homework for this lecture, and I discovered, some of you may or may not know, that my work is about Boltzmann, the prize is about Beltrami, which actually I knew Beltrami, of course, mostly because of the beautiful pseudospheres. But when I did the exercise, I discovered 2 things. First, that Beltrami has done a lot of important contributions which are very modern. For instance, the Laplace-Beltrami operator is currently used to solve PDEs on manifolds, and this has many important applications in optimal shape design. The single eigenvalue decomposition, which is a basic tool in engineering and also in quantum computing, I recently figured out, also carries Beltrami contribution, and the Beltrami flows are very important for topological fluids. So, I mean, it looks like Beltrami really had work which is lasting the test of time. Boltzmann needs no introduction, but I realized they are basically contemporaries, right? So the question came to me as to whether, by some chance, they might have crossed paths. And I looked into this possibility, and I discovered this beautiful paper. I don't know Riccardo Rosso, but that's a very nice paper. And where it informs us that Beltrami at some point was concerned with thermodynamics. Boltzmann, of course, laid down the microscopic foundation of thermodynamics. But he approached thermodynamics from the point of view of Truesdell, rational mechanics, namely using continuum field theory. And at some point in the abstract, as you can probably read, Beltrami occupied himself with kinetic theory, but he never mentioned probability. At that point, honestly, I gave up, because, as you know, Boltzmann physics is basically the cornerstone of Boltzmann physics is probability. So I have to conclude that, unfortunately, the 2 contemporaries didn't really interact into any significant extent. Too bad, but that's it. So now the story, the Lattice Boltzmann story. Roberto, you stop me. I have a lot of material, but I can skip or stop anytime. So let's begin from the Jurassics. And the Jurassics, as I said, we are talking mid-80s. Some of you were not yet born. I was, and so was Massimo as well, by the way. And it began, it's a nice story because there is a lot of serendipity.
Sauro, you start already for all the time from the Jurassic because of your name.
Because of my name, yes. Yes. And the question is which one I am in the future. I don't know either. Well, how it all began, and that I think is useful for the young people and not so young people young people of any age in this room, because it really had to do with some very nonlinear aspect of life. Here comes one. So back then, I was coming back to Italy from Switzerland, and my PhD was not yet completed. And I was working in IBM, European Center of Scientific Engineering Computing, beautiful place. My boss was Roberto Benzi. Some of you know him. He had a group called Fluid Dynamics. And I was just beginning doing some work in that direction. At some point, the boss of Roberto, Piero Sguazzaro, stepped into my office and said, Sauro, I've seen this paper. Why don't you take a look? This is cellular automata for fluid dynamics, 1986. Okay? But the main reason was that I was supposed to learn how to program the IBM machine, which I did. Actually, those days I even did some assembly exercise. Yes, it was Piero.
No, you never demanded.
Okay, that's of course Massimo. No, I did to the point that, in fact, I discovered even multi-spin code in Massimo in Forte. And so I, in fact, repeated this exercise. And of course, I could not find any Navier-Stokes solution. The simple reason being that on this lattice, you cannot find fluid dynamics, because as you may notice, there are just 4 leaves. Okay? And these 4 leaves, some of you know, and for the others, this is the news, you cannot solve nonlinear fluid equation because you don't have enough rotational sync. In those days, I had no clue. I really didn't understand the point at all. And my reaction was, come on, give me a break. If I take enough grid points, I will retrieve fluid dynamics. And of course, I did it. The reason being that, and please take a look at the date. This is PRL, April, 21 April 1986. Ahead of this paper, there was a real paper. And the real paper, as you can see, there is a change, minimal change of symmetry. You go from square to absolute. And that's enough to deliver Navier-Stokes, which is interesting. Right? It's like trivial thing. What is the difference between a square and an hexagon? Well, there is a small surplus of isotropy in this lattice, and this little surprise makes a completely different story. Here you can solve Navier-Stokes. This paper was a big one, and many big people got involved in those days. Stephen Wolfram, which is the mathematical Wolfram, there is, that would be for the History Center, quarrel, because Wolfram claimed that it was his discovery, which was stopped by PRL in favor of, well, I shouldn't say that because it's too much, it's in the stream. But anyway, it was an interesting, it was a competition, let me put it this way. And the competition was very harsh because people felt it was a big deal. Okay? Because in principle, with cellular automata, you could solve, I give you the bottom line, fluid dynamics in terms of Boolean algebra, so no round-off error. It was an exact way of computing fluids, and meaning that potentially, and it was very amenable to parallel computing, to the point that, and Feynman himself got involved in the latest stage of his life. At some point, on the Washington Post, there was an article saying this is so important that should be kept out of the Soviet hands. Don't forget, 1986, the Berlin Wall is standing. And I would say it reminds a little bit of what is going back to days when now we see with GPU, NVIDIA, with machine learning that between China and the US. But just to give you a sense of how important this was regarded at the time. Now, of course, I have no time to go into the details, but the bottom line is that you basically solve an equation which the left-hand side is basically the free streaming of particles, but the particles here are bits, 0, 1. So either you are sitting on the left side, 1, or you're not, or you're not. And there are 6 possible directions for the motion. So the left-hand side is just the motion from one lattice side to another, and the right-hand side is how these bits interact with each other. The key point, which is by no means trivial at all, is that these NIs are Boolean occupation number, like Fermat's in condensed matter. 0 and 1, nothing else. And the remarkable thing is that you can boil down an expression for the collision operator, which is compatible with the Boolean nature of the game. If you do the algebra, I just sketched it there. I don't know whether you can see a reaction Ij going to KL. The idea is that you should have a particle in state J, a part and particle in state J, and you should have no particle in state K and L because you have to fill this state. And if they are permanent, so they are already occupied, there is no possible collision. By suitable combination of this type of operators, and there are operators for 2-body collisions, 3-body, up to 6-body, you construct this collision operator, and this operation takes only value -0 and +1, so it's compatible with the Boolean nature of the game. Big deal. Unfortunately, when you took a closer sight at this game, many important shortcomings were emerging, and that's how lattice boson was born. I will not really go into any detail, but essentially the way lattice boson was born is item number 1, because being Boolean numbers, you were swimming in the north. Okay? It took a lot of automata to generate a meaningful signal. And this is a very old picture, again, coming back to Roberto. This was my first PRL in 1988. And we ran I still remember, it was a lot of fun. This was a huge calculation by then. We had big machine by then, in those days, 8,000 by 8,000 automata. And I still remember how happy we were when we saw that the vortices were, not only were there, but they were moving quantitatively correct. This paper is not very well known, but I think it was really very early, one of the earliest demonstrations that the lattice gas would work. But look at the right side. This was Roberto, the very same days, using pseudospectral methods. And you can judge by yourself the difference. They were much more accurate and at least 3 orders of magnitude faster. So I remember the boss, the IBM boss, said, very nice work, guys, please switch to something else. Okay. But, and that's where nonlinearity of life came into play. Obviously, Vanetti, he must be credited for realizing that if you want to do fluid dynamics, you don't need to do all these very costly collisions. You can directly move to the Boltzmann level and get rid of the noise beforehand. So the lattice Boltzmann is basically a noiseless lattice gas, both as Dan Frankel, which is a very important statistical physicist, he calls it pre-average lattice gas. That's what it is. You can formulate the theory, take this collision operator, which is exact, and average, take an ensemble average of the lattice gas collision, and do the crime. The crime is to replace the average, move the average inside, which you cannot do because it's non-linear, and forget about it. That's exactly what Boltzmann does in continuum kinetic theory. It gets rid of many body correlations. But many body correlations are not needed to generate fluid dynamics from the microscopic level. And Gianluigi Vanetti, unfortunately, died in a very sad crash, in a plane crash. They realized it first, but they didn't pursue the lattice Boltzmann as a computational tool. Somehow they didn't see the fact that, yes, it is noiseless, but it can be used as an effective computation tool. And the big smile of Lady Luck to me came in 1988. Javier Jimenez was an IBM, part-time IBM working in Madrid, and he sent me one of his students, Francisco Higuera. I don't know, Massimo, you were not, you were there. And Francisco came, and again, I really like to give the credit because the lattice Boltzmann is not, certainly not a one-man story. It's really many people contributed. Francisco came to me, I don't know whether you can spot the figures over there. This was sort of museum of science. These were the graphics that Francisco came, brought along from Madrid, say, look, Sauro, stop doing the lattice gas, we have something better for you. Okay. I was still in my, German and Swiss PhD state of mind. I was doing my job with lattice gas. I wanted to get my job finished before doing something else. But happily enough, in the end, my Italian nature prevailed, and I switched to lattice Boltzmann. They realized that, again, this would be a long story, but essentially the idea is that in order to recover the Navier-Stokes equation, you don't need the molecular effect. So the idea is that you formulate the collision operator in terms of relaxation. These are relaxation rates, if you want, of the actual Boltzmann distribution function, the probability for a particle to move along direction J, and J runs on the lattice, the same lattice I showed before, and you relax it to a local equilibrium, which depends on, in a very well-known way, on the density and velocity of the fluid. Okay? But the density and the velocity of the fluid can be computed. The density is just the sum of all the particles moving along all possible directions. And if you sum the momenta of the particle, okay, which are also known, you generate the velocity. So this is a self-consistent relaxation. The big deal is that you know this object, and all you have to do is a matrix vector product. Meaning that instead of having a complexity, V is the number of bits. In 3 dimensions, you would need 24 in those days. So on each point of the lattice, on each instant in time, you have to do 2 to the power 24 collisions, 16 mega, which was a lot. Those days was unthinkable, and still today would be. A typical computation for dynamic code takes 1,000 operations per bit point times 10. This here we are talking 10 minutes. Instead of 2 to 24, we have a matrix vector product, so we have 24 squared, which is a totally different game. So this, to me, it was one of the most important breakthroughs in the subject. And when Francisco came and visited, we produced the first, actually, this is the very first lattice-Boltzmann simulation ever published in a journal. And as you see, we basically quantified the intuition. This paper, was published in, I think in 89, and it is actually the way we validated the idea in a quantitative terms. And then came another breakthrough, and Roberto was my boss, and he came, having seen the results, said, look guys, since we now work with this formula, and all you have to do is to recover the Navier-Stokes equation. Why don't you design the collision matrix top-down? Looks like obvious, but you know, science is like that. Many obvious things are only obvious afterward. And we did the job. You basically take the matrix, you know the symmetries that the matrix has to fulfill in order to recover Navier-Stokes, and you basically compute the eigenvectors, A, I, K, blah, 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 and you choose basically the eigenvalues in such a way. Now, I have to tell you many things in a short time, but you will not be surprised to hear the leading non-zero eigenvalue control the viscosity. And the viscosity was a problem because, as I said before, if you are in a lattice like this, there are very few collisions which are compatible with mass, momentum, and energy conservation, meaning that the particles do not collide much, meaning that they diffuse a lot, and high diffusivity means low Reynolds number. The Reynolds number is the velocity times the length divided the viscosity. The lattice gas has an enormous diffusivity. It could only simulate very low Reynolds number, no use. By the time you turn to the top down, the very first omega there will give you an angle on the viscosity. So we could choose the viscosity instead of, and so we had the lattice-Boltzmann standalone, and that was the paper which really brought lattice-Boltzmann on. At that point, we were competitive with spectral, finite difference, etc., etc. So the top-down formulation was a second breakthrough, and was met of a few months later. It all happened in a very short amount of time. And with that code, again, I mean, I don't want to go into detail, that would be obscure, but the carry-on, the take-home message is that with that, we were competitive with respectable fluid dynamics. And then we started to do some application. I remember this. Flows in porous media is still one of the best applications of lattice-Boltzmann. This is a very primitive porous media, as you can see, but still this was 1989. And with Roberto, we were hoping, actually, that we could go actually to zero viscosity, which of course you cannot in any finite lattice. But just to say that since he was working so much in turbulence, what we tried to do was mostly turbulent flows. And here is again how nonlinear life is. A few years later, 1992, a group at École Normale, they realized that as long as you deal with incompressible flows where the only parameter is the viscosity, there is really no reason to be working with a matrix. All you need is just one free parameter, and they published basically this is called lattice BGK because it comes from Batnagar-Gross-Crook. It did the same approximation in Boltzmann kinetic theory. And the big advantage is that you just have a one relaxation parameter instead of the full matrix. And this is still actually the most popular lattice Boltzmann in town. And they also gave actually the systematic expression of the local equilibrium, which is fully general. C sub I are the discrete velocity in the lattice. Rho and U are self-consistently computed out of the population. And so with this formula, you have the algorithm is ready for you. And that's why this paper is one of the most cited. By now, I think it has 3,000–4,000 citations. And much to my shame, I remember that Massimo Vergassola, some of you may know him, who was a very brilliant student in those days, always told us, but why don't we still using the matrix? And I said, who cares? Well, actually, we lost a big opportunity because we could have very well done this job. It was just next year. Just to see that, to show you that sometimes there are kind of obvious things and you don't do it because they look basically trivial. And so never underestimate. If something is simple, doesn't mean that you shouldn't pursue it, because sometimes that's exactly where you get the best payoff. Anyway, so this is, and then came another point. The point was that, again, I have to make a long story short, but there is a big crime that we committed when doing the top-down approach. Because we did not simulate collision. We postulated the existence of a local equilibrium, okay? But by the time you do that, you can, in the local equilibrium, you can encode mass, momentum, and energy conservation, but you say nothing about the second principle. There is no guarantee whatsoever that this will be stable. And the reason why it worked was a sort of lucky strike, because we didn't realize that finally this scheme does have an H theorem, like in Boltzmann kinetic theory, but we didn't think of it at all. It was only 1996, Ilya was visiting here at IAC, and the reason why I put up Daniela's picture, because basically in those days she came with a nice suggestion on how to do crystal growth, which was a very successful application. Still, the paper is still going pretty well. So all I'm saying is that the lucky strike was that we had an H theorem without realizing it. And proving that the lattice BGK has an H theorem is not trivial. This is mostly Carlin, and Carlin then made a career out of the so-called entropic lattice Boltzmann method, because the entropic lattice Boltzmann method is much more stable. Okay? If I don't have the slide here, but let me just tell. Oh no, I do have this. The reason, I mean, it's simple enough for me to explain very quickly. You see the point. If I start with F positive and F equilibrium positive, as long as omega is between 0 and 1, I'm sure that this guy will be positive as well. But in order for running very low viscosities as needed for turbulent flows, I tell you without proof, but it wouldn't be difficult, you have to put omega 2 minus epsilon. You have to work very much in the over-relaxation regime, where you have no guarantee that starting from positive F and positive F equilibrium would return a positive. And we were consistently working in the unprotected region, and it worked. In fact, it worked up to a point. I remember that it worked up to omega 1.89, I still remember, which I used to call the Benzi constant, because we didn't know why beyond this value the code would crash, but later we understood, because then at some point you crashed the H theorem, but we were not supposed to work in this regime. We were supposed to work between 0 and 1, where the Reynolds number would have been miserable. So again, lucky strike that there was an H theorem. And ever since, well, of course, is that be perfect? Not at all. There are many issues. I would say still, if you want to do a body fit geometry, I don't think that is, you can do it, but I mean, then you lose the basic power of the method. It's still comparatively difficult to do compressible calculation with strong heat release, etc., etc. But by and large, the method is very powerful. And so this is, I think, the nice story, which I think would please Beltrami, because we started in 1986. This was the kind of flow that you got from lattice gas cellular automata. Very exciting from the computational point of view. Feynman was fascinated by the fact that you saw structure there, but the CFD people would laugh at you, right? What kind of... Then, in just a matter of a couple of years, we got something reasonable, but still, I mean, we were competing, but we are not superior to CFD. And all the way to the 20s, this is a landing aircraft. This is real engineering. This is a commercial code, and I think I have to credit Stephen Horsack, whom some of you certainly know, who unfortunately passed away far too early. And he was a strong advocate of the method. How to do turbulence bonding with lattice-Boltzmann, that would be a thick topic. But I mean, this shows you a very nice trajectory where, in fact, statistical physics, applied math, high-performance computing all came together to generate what I would call an engineering tool. That's what it is. And ever since, there are so many applications across scale of motion, racing cars, hemodynamics, phones, etc., etc. And I would say that if we have to come to closer to what we use lattice-Boltzmann today for, Leo Kadanoff, again, very prominent statistical physicist, was very interested in the early 80s. He thought that lattice-Boltzmann, lattice gas, not lattice-Boltzmann, would have been a simple model for complex flows. But as a matter of fact, no. I mean, you cannot use, you have to add some complexity to your scheme in order to do simulation like this, simulation where you have a flow with a lot of interface. And here there are two major developments. One is due to Tony Ladd. He developed lattice-Boltzmann with fluctuation to address nanoflows and to address how to move actually rigid particles into the lattice-Boltzmann flow. And this is today one of the mainstream of lattice-Boltzmann. The second mainstream is how to insert potential energy, non-ideal fluids. Shang Chen is, I think, by now probably the most cited paper. It's very simple. You just add an interaction between, there are many smart ideas behind this simple expression, but essentially they could show that you can introduce an effective force between the lattice side at a given lattice side and the nearest neighbor. Is a sort of minimal potential energy model. And with this minimal potential energy model, you can generate interfaces. And the interfaces pop out of their own. That's a major advantage. You don't need to track, which would be a nightmare. Imagine a tracking algorithm for a flow like this, where there is much more, the surface to volume ratio is extremely high. That would be a total nightmare. When you run the simulation, the interface just pops up for you, provided you code up the interaction. But the interaction is still nearest neighbor, like this, you see? So with an extra 20 lines of code, you move to single-phase flows to multi-phase flows like this, which is a major practical advantage. And those of you who have coded lattice-Boltzmann know that you can do multi-phase codes with the next routine with 20 lines of code. So that was a time where people would still claim, and I would say, Roberto, it was mostly the applied mathematics community, they were claiming that we were doing uncontrolled approximations, okay? Which was not true, because we were doing approximation, but they were not out of control. So the statement was, and it was a diktat in PRL, there was a paper by a Chinese mathematician, which I will not mention, says you should never, because you cannot use Lattice-Boltzmann other than for Navier-Stokes fluid. But there is a rural region, in fact, especially in soft matter, where you are too small for the continuum treatment and you are too large for molecular dynamics. And I would say that as of today, soft matter is the region where, in fact, you have most of these cases. And the soft matter has turned out to be a gold mine for mesoscale techniques like Lattice-Boltzmann, which are in between continuum and atomistic. And I have to say that, Roberto, you tell me if I'm wrong, but kinetic theory was still perceived up to some 20 years ago as a corner where you do rarefied gas dynamics, where you use the real Boltzmann equation, and nobody really suspected that you can use it where, in fact, the continuum assumption is shaky, but still molecular dynamics would be an overkill. And that's exactly where Lattice-Boltzmann should be used for. And that's exactly where the long-lasting contribution might be used. This no-fly region, and even in the books, you know, again, kinetic theory is mostly presented for rarefied. Now it's changing, okay? But mostly presented as a tool for rarefied gas dynamics. I think the most important contribution of Lattice-Boltzmann is to show that no, you can use it as a very effective tool to cover this no-fly region between the atomistic and the continuum. Of course, you have to do it very carefully, because it is true that you don't have any backup theory. Those of you who know kinetic theory, you know Chapman-Enskun method, etc. Well, you show that you converge to Navier-Stokes. I am not aware of any result which would show that you converge to the proper macroscopic equation when you have this kind of interfaces, etc. Sometimes the equations are not even known. So it is true that you have to be cautious, but nevertheless, it is also true that if you have full analytical backup, where is the fun? Right? If you already know the solution, what's the point of using the tool? So it is true that you have to be careful and very, very critical of what you get out of the computer, but it's also true that you have a beautiful instrument to ask in very complex endeavors, where in fact a continued discretization would be much more unwieldy and most likely much efficient. So unfortunately, you have to put up Massimo, who is nasty, as you know, but we must admit, I'm very sorry, I have to admit publicly he's very good. And with Massimo and Simone, we had a great time in connection with thinkers here in Harvard, and this is really their credit. We using actually technology in a broad sense of moving object into flows, into Lattice-Boltzmann flows. There has been a beautiful story for which I should take really no credit. We did first biopolymer translocation, blood flow simulation with finite size particles. This is a really complicated application. And later on, Simone, I think, did also protein crowding. I still remember this paper. I think this was one of the most impressive large-scale applications. And they made it to the Gordon Bell final. I think Massimo holds the world record of the Gordon Bell finals, but Gordon Bell is the most important supercomputing contest worldwide. I think it's still running. But unfortunately, just to get it, I'm afraid, is not only a matter of science. But nevertheless, just to say that, I mean, we are talking 2013, 10 years ago, more than 10 years, and we are already talking petaflops on realistic geometry. This was real human arteries. And Simone remembers very well all the discussion with the Brigham School. I think Simone was there. Andato. Okay, too bad. I mean, this was really very complex simulation and really high performance. Actually, we extrapolated that if the code was called Murphy could have been extrapolated, it would have reached the exascale line in 2015. That didn't happen for many reasons, including the fact that, I mean, maintaining and developing this kind of complex software it's really very demanding enterprise. But just to say that there was really a very significant activity in the HPC side of the story. And along more or less the same line, much more recently, Giorgio, who was in fact a postdoc from Renzo Piva many, many years ago, he maintains a code, high-performance lattice-Boltzmann code, and just in 2021 we did this calculation of the flow inside a sponge, which lives at minus 500 meters in the deep sea. And the question is, how does the sponge manage to survive? And in performing this, this is a 5 billion grid points simulation, so it's a large-scale simulation. We actually had reason to believe that due to the synergy between the structure of the sponge, which is really amazing. Okay, if you look into this structure, it really looks like there is a lot of hierarchical design. There is a sort of synergy by which the sponge is able somehow to trap the water inside, and this in principle helps both feeding, food, so survival, and also sexual reproduction, because the sponge is young. So marine biologists in the team suggested that fluid and structure as a sort of synergetic cooperation to facilitate life in the abyss. And I think this was the only reason why we could make it to nature with pure simulation, which is a rather rare event. And here I credit Giacomo cannot come. He just told me that he has a family. But I think Giacomo and Giorgio deserve the credit for this HPC performance. And then, okay, how much time do I have, Roberto? I think I can be very quick. Then we discover how to, you know, make things a little. This is a typical lattice you would use for fluids. This is not a cartoon. That's what you do. You have 18 discrete speeds. And one thing which, the most important thing I forgot to tell you, actually, I take the opportunity now. If I had to say what is the secret of lattice-Boltzmann in one word, the secret is here. You know, in Navier-Stokes you have U grad U, right? Meaning that you move the momentum along a trajectory which is curved, because the trajectory is given by the velocity itself. Okay? So if U is a complex field, fluctuating, turbulent, perform, etc., you have to move information, or you have to ride a very wild horse. In lattice-Boltzmann, you never have to do that, because you work in 6 dimensions. X, Y, Z, and 3 coordinates for the velocity. In the early days, I forgot this to tell you in the beginning, for at least 5 years, each time you went to a conference presenting lattice-Boltzmann, they say, are you really so understood? You must be mad, crazy, because we have a problem in 3 plus 1D, 3 space dimension plus time, and you go to kinetic theory where you have 6 dimensions. This is totally stupid. The reason why it is not stupid is because, remember the streaming. The streaming means that if I have a right moving particle, like in the cellular automata, here there is full continuity with lattice gas, I'm blind, I'm not thinking. When the clock comes, I move right. And if I'm a front mover, I do that. And this information transfer always goes that way, along straight lines. And you always land on another lattice side. So the information always moves along straight lines, regardless of the complexity of the macroscopic field. This is a major advantage. And this, like in the lattice gas, is still an exact operation because it's a memory shift, not floating point. So the transport part in kinetic theory, in the lattice kinetic theory, is exact, computer-wise. As opposed to U grad U, where you have to take your floating point operation. So I think this is still something that Lattice-Boltzmann has inherited from the lattice gas picture. And I think is the major strength of the method. And it would not be possible unless you go to higher dimensions. So it's yet another instance where higher dimensions look like a nightmare, but in fact they provide you an advantage. Okay? So we use these lattice, high-order lattices for many applications, and here I think in most recent time, this is a feature I really like very much, not because of the science we did with it, which is nevertheless interesting, because out of this project we got the ERC in 2017, but we got another 2 ERCs, the small one, proof of concept, and lately, starting this month, a Pathfinder, which is the industrial version of the ERC. But, and okay, that would be many talks on its own, how to design materials out of microfluids based on droplets. When we started, this looked like a simple thing to do, but no Lattice-Boltzmann would have been able to do this because the droplets would have merged. So I think Andrea Montessori was mostly responsible, but in fact, for the Lattice-Boltzmann, which prevents merging. But the reason why I like this picture is because, well, Fabio Bonacorso, you don't know, is a Torregata, Pieno, you know, but Andrea, Marco, and Adriano. Andrea got an associate professor straight from postdoc position in Roma 3. Marco is a primo ricercatore here, and so is Adriano. So during this ERC, and I'm very happy to announce the cooperation with Roberto and also with Emilio Campana, we had the chance to get, oh, thank you. We had the chance to generate permanent positions, and I think that was a good use of the ERC money. And now we still cooperate, less tightly, of course, but this, to me, this was a very, very rewarding experience. We are still actually running. Marco and Adriano ran this, the second POC, and me, which is a student at postdoc at IIT, will help me with the Pathfinder. So just to say that this is still an outcome of the Lattice-Boltzmann for complex flows, okay, in a very generalized sense, but follows on that line. I don't think I should talk about relativistic, but let me spend just a few final words about what keeps me busy mostly firsthand these days, you know, the PNRR and the quantum computing. So at some point IIT asked me, well, why don't you take a look at quantum computing within the PNRR? So why not? And we decided to do something rather weird, which is trying to do fluid dynamics computing. Now that would be another talk, but you know that quantum computing usually has been invoked by Feynman to do quantum problems. Famous statement, nature is not classical. If you want to simulate nature, you should use quantum computers. But Feynman was mostly referring, this is a quadrant. In the horizontal line, you have CC means classical computer for classical physics. CQ means classical computer for quantum physics. And that's how we do simulation as we speak. This is 99.9% of the simulation work. The quantum computing usually is, the quantum computing that Feynman invoked was basically this. CQ is the many-body Schrödinger equation, which is almost a mission impossible because it's a problem which lives in hundreds of thousands dimensions, and you cannot solve a problem with so many dimensions with grid methods, and even Monte Carlo has its fair share of trouble. So Feynman says, don't solve the many-body Schrödinger equation on an electronic computer, develop a quantum algorithm. And this, as we all know, has its fair share of problems. But what we are trying to do is even worse. We are trying to use quantum computer for classical problems, and not just classical, but like Navier-Stokes, where they are nonlinear and distributed. And you know that quantum mechanics, quantum computing is rooted into the fact that quantum mechanics is linear, a concept, a universe. So in these days, I'm struggling with, and wherever we're struggling with how to code a nonlinear and non-unitary problem into quantum computing, it's a lot of fun, but it's also very frustrating because you find a wall, you turn around the wall, and there is another wall. That is very technical, but let me tell you, there is a technique, you might have heard, Kahneman embedding. It basically transforms any finite dimensional nonlinear problem into an infinite dimensional linear one. So we said, okay, at least let's turn around nonlinearity. And when we ran the Lattice-Boltzmann with Kahneman, it is excellent. Navier-Stokes would be a nightmare. Lattice-Boltzmann is pretty good at Kahneman linearization on classical computers. But when you try to move to the quantum, which is the real story, you meet with the, I mean, I don't want to be technical, all sorts of complexity. And so far, it's just like a slalom. We have a circuit which is very deep, so you will be killed by the quantum noise. We find a way of reducing the circuit depth, but then it turns out that the calculation becomes probabilistic and the probability of success is miserable. And then you want to lower, enhance the probability of success. There is a series of algorithms called amplitude amplification. I just give the names, it's very technical. And they enhance this success probability, but only if your matrix is unitary. So now we are trying to turn around and generate an amplitude amplification algorithm for non-unitary update. And honestly, I don't know whether we will ever succeed. But it's a very rewarding exercise from the intellectual point of view. Whether we will ever end up with a viable quantum algorithm for fluids, honestly, I do not know. But it's fun. So this was a long ride, covering 3 decades and a half. There is still a lot of things to do. But I mean, one obvious thing to do is to enhance the Lattice-Boltzmann that we are using today with machine learning model to do even more complex flows. Kinetic models of fluid turbulence is very technical, I didn't mention, but there is a lot of work to be done to improve this, the codes which are used in the commercial version of Lattice-Boltzmann. In the nanofluidics, we do not know how to treat strong fluctuation. Just to say that there are still many items where, even though the topic is very mature, there is still a significant amount of work to be performed. So I think I'm almost over with my time. So thanks time. And this is an articulated thanks. And don't look at that because I'm sure I forgot some name, okay? But just to mention that, as I said, this is certainly not a one-man show, and during the years, and I really mean it, I have been profiting of the collaboration with so many bright people who have taught me much more than I could even imagine, and I think Rome has been instrumental in this respect. It's a fatiguing city, as we all know, but at least you can always find good people, very good people. I could have not done that in any other places. And of course, I have to thank the committee, my nominators, Michele Benzis, whom I don't know, Giorgio Parisio, no, Roberto, of course, and also because during my more than 20 years stay in IAC, I could enjoy really a lot of, that's basically the bulk of my career. So I'm very grateful that I could develop my scientific career here at IAC. And of course, George is not here, but I owe him some special thanks. First of all, the fact that to me, it's still unusual that you have as a laudatio the letter by George, which is kind of embarrassing, but I am very, very pleased. And I have to say, George is not here, but maybe never doesn't change anything. He has been really constantly supporting and very friendly to me. I'm really grateful to him. And not only to me, I think George is really very important for all our community in general, meaning statistical physics, high-performance computing, and applied maths. I think he is really playing a very major role in giving dignity and dignifying this community. So I'm sorry it's not here, but I'm very grateful nonetheless. And of course, as I used to say, lately, thanks to Ludwig, because it's like the espresso, no Boltzmann, no Lattice Boltzmann. So he really did it. And I'm sure that if he had had a computer, he would have invented Lattice Boltzmann in no time, because if you look into his horrible book, I mean, horrible, says super thick, The Kinetic Theory of Gases, he writes explicitly in a discrete velocity version, and he said, this has probably even more physical meaning. So it was there, no question. Okay. Maybe he would have not thought of fluids, but I'm pretty sure that Boltzmann with the computer would have invented Lattice Boltzmann overnight. And of course, that's been a long ride over several institutions, and of course, I'm grateful to them all, and particularly the Italian Institute of Technology, that's where I am for a few years, and of course the CNR, where I spent basically the bulk of the story, which I just been telling. Thank you.
Thank you, Sauro, but maybe we can have some questions, comments. Massimo.
That's going to be nasty.
I'm not going to ask you if you, in the end, learn AI. I'm not going to ask that.
Yeah.
I already know the answer. But let me ask you
a
bit more serious question. You mentioned a number of advancements in terms of application of the Lattice Boltzmann method. But in the very end, we are still using the original, say, algorithmic approach, combining the collision screening and so on. If you remember, we did together some attempt to follow a completely different route using an implicit approach. I don't know if the implicit approach can still be considered a possible candidate, but do you see any possible advancement in the algorithmic side for Lattice Boltzmann, also in view of possible different computing architecture?
Well, yes. I mean, if you refer to the matrix version, you remember why we abandoned, right? I have to say that I have not seen any work in that direction, so I don't know why, exactly why, but I think that still the initial intuition that Lattice Boltzmann is good as long as you can keep it simple, still. Now, honestly, Massimo, you know better than anybody else how good the method is in GPUs. To me, and come back to the very last slide, if you could move it to the QPU, and I mean, I've not been at the too many topics in this talk, but the point, it is not real. When you do this Kalman story is, it would take me a few minutes, but essentially you take a nonlinear problem. Let me tell you what, yeah, each drop equals x squared, okay, which is nonlinear. Then you say, okay, I call x x1, and I call x squared x2, which means x1 dot equals x2, and this is linear. Right? Looks like a joke, but it's not, because then you write x dot 2 and you write x3, and you generate an infinite. When you do that for the logistic equation, it's a piece of cake. When you do that for Navier-Stokes, it's a nightmare. When you do that for Lattice Boltzmann, it's a piece of cake again. So classically, this works like a charm. The quantum algorithm, no. To me, if you ask me about algorithm, if I had a click on something that I would like to see solved, that would be it. And actually, we might be discussing that now, because the more I go into it, the more I'm dealing with matrix algebra. And I know that in your course here, you just emphasize it is true. I mean, you think you know matrix algebra, you do quantum computing, and in the end, at least me, I discovered how ignorant I was. So then it's only matrix algebra time and time again. So if you could find a trick, now we are doing this sparse matrices, blocking, coding, and it's all about linearity. If you could find a way to formulate a quantum algorithm for the Kalman of the Boltzmann, to me that would be it. For the classical part, you are right. I mean, I don't know, maybe Mark or somebody else wants to comment. No, I don't believe it. It's all about new boundary conditions. Nuccia, I'm sorry I didn't mention the work, but she's responsible for a very nice application with the open boundary condition. I'm not following the details.
Thermal problems. Can you say something on thermal problems for the students?
Well,
because thermal problems.
Thermal problems to me are still difficult, but you know better. I have not been dealing with thermal problems for the last many years, probably since before. I see that there are simulations around, but I mean, maybe
Okay.
Is there any major algorithm that advance in that direction?
No, I think no. Many velocities, many speeds of velocities, double populations, but we are not there.
It's always amazing the same, it's still a collide. So I don't think, in that respect, in my opinion, that the algorithm is basically stable. Of course, you could add a lot of, I think one should couple to machine learning to devise better pseudo potential, like they do in mathematics. They don't have the resources to do that. But algorithmic activities. And even on GPU, I don't know if there are any. I mean, Marco and Andrea, they are now doing this, but I would still regard it as the same story. It's always based on string and that. I mean, there are very clever technical advances there, but I don't think there is a major paradigm shift in the algorithm.
Unless you want to think about the possibility to eliminate the storage of the populations, but this is a problem more related to the GPU architecture. The fact that now moving memory is something that is a really
Yeah, but Watson is not good at that. Watson has a lot of memory.
yeah, for this reason, it is better to move just the hydrodynamic space and then repeat the median projection at each time step.
But actually, this is the POC I was mentioning. It's called LB fast, and it's basically high performance. So no, for the thermal part, which I'm not following, but I see that people do thermal simulation, but I don't think there is a major development around this line. And nowadays, it's a lot of things, and I don't follow the research on microfluidics, droplets on corrugation, and this is where the method is, I think, there to stay.
Although the thermal part was involved in critical growth exploration.
But we cheated there. I mean, cheated in an honest way, in the sense that we were using it in two populations, which is a way of mimicking a temperature. It's an intelligent way, but I don't think it's really based on the physics of temperature. I remember we were representing the fluons, of what we call also the fluid particle, and thermal particle, we call them phonons. And we couple the two populations, which is a nice idea, but it does really, I don't think it's one-to-one related to the real physics. It's a nice trick. The paper is still people read it.
Maybe the real physics is many speeds to mimic the temperature concept.
Yeah.
Okay.
So it's a nice trick. Sometimes it works, but if you have stronger changes, for instance, if you have a combustion engine, I don't think there is any application. Again, I mean, it's not perfect. Nobody is perfect. And I think it's already doing a lot of good stuff. But to me, coming back to Massimo, my wish would be that we could formulate something. There's more breakthrough in quantum computing. That would be really satisfying. I'm not sure. I wasn't clear.
Okay, so thank you guys. Thanks to MEMOCS to organize this prize. Cerco dell'Isola and collaborators are here today. And okay, we are honored to host all this prize you are
You are
organizing in this Okay, thank you very much.